This video deals with the fundamentals of trigonometry, and to start with we're going to look at the concept of an angle. And just as a definition, an angle is a measure of the degree of separation between two lines. But an angle measures this degree of separation along a circular path. So it's a rotational kind of measurement. So if you think about it by considering this set of two lines here, so we have a point here. These two lines emanate from the same point. Now the angle between these two lines is characterized by the amount of rotation required to get from one line to the other. If I carry out a complete rotation, I get a circle. So this is just a rough sketch. But if you also consider this pair of lines emanating from the same point, an angle characterizes this degree of separation along a circular path. Here again, we also have another angle here, which characterizes the degree of separation between these two lines emanating from the same point. To just demonstrate the main idea, consider this line, and then consider this blue line emanating from this point. I'm going to call this point, give it a name, call this point P. And then consider another line. This line will be green. Now, if I'm moving, or you're moving along a circular path from this black line, you get to the blue line first, and then you get to the green line at some point. Now, the degree of separation between the black line and the green line is greater than the degree of separation between the black line and the blue line in an angular sense, in a rotational sense, because I have to rotate more to get to the green line than to get to the blue line. And that's the main idea. So an angle just measures this degree of separation. So I'm pretty sure you must have come across angles. So for instance, you can have a case here. Let's say this angle is 30 degrees. You can have another angle like this, where this angle is 120 degrees, for instance. You can see that even just by inspection, you can see that the degree of separation between the two lines in this case, emanating from this point, is greater than the degree of separation between the two lines in this case. And the way that's characterized is by the angles. Here, the angle here is set to be 120 degrees, and the angle here is set to be 30 degrees. Clearly, the larger the angle, the larger the degree of separation. I'll show you another angle. Here's another one. Degree of separation is really large. Here, this angle could be 30 degrees, for instance. So the larger the angle, the larger the degree of separation. Now, an angle has the units of degrees. One of the units of angles is degrees, and that's the one we're going to be sticking to. But the key point here is an angle is a measure of the degree of separation between two lines emanating from the same point. So you have a point, you have two lines emanating from that point. Degree of separation along a rotational path is measured by an angle. The larger an angle, the larger the degree of separation between the two lines emanating from the same point. The smaller the angle, the smaller the degree of separation between the two lines in a rotational sense. And that's the main idea. Now that you have, at the very least, an idea of what an angle is and does, we can now take a look at common angles that you will encounter. You need to remember these, and we're going to start with the right angle. A right angle is an angle of 90 degrees and is the angle formed between two lines that are perpendicular, and it's represented with this sort of square sign, this symbol here, which is shaded. So this square represents a right angle. So here's one right angle, this square here in black. Here's another right angle in red. Here's another right angle blue here, and the white box also represents a right angle. So anywhere you see this symbol, you know you have a right angle. Here we have a right angle triangle, which you've come across. So it's a triangle that has one angle that's equal to 90 degrees. That's a right angle triangle. But that's really all you need to know about a right angle. It's an angle of 90 degrees and it has a symbol. Next we have an angle on a straight line, which is an angle of 180 degrees. So the angle formed on a straight line, the complete angle formed in a straight line. So it's usually represented with this semicircle symbol. And just one thing I want you to notice, that an angle on a straight line, which is an angle of 180 degrees, is also equivalent to two right angles two angles of 90 degrees. So this angle here is 90 degrees. This angle here is also 90 degrees. And I mean, this is a complete angle on a straight line. And like 90 plus 90 is 180. So anyway, the common representation is this semicircle about a straight line. That's an angle on a straight line. 180 degrees. And just as a form of revision of your junior secondary school maths, you know that if you have an angle on a straight line split into a number of parts, so I'm just gonna shade this blue. So that's one angle, blue here, and here's another angle in red, and we have one still left in yellow. We know that if this angle is angle x, for instance, and this angle is angle y, and this angle is angle z, x plus y plus z must be equal to 180 degrees, because on a straight line, the complete angle on a straight line is 180 degrees. If you break it down into fragments, in this case 3 fragments, so 3 different angles, 3 smaller angles, 3 sort of, can I say, sub angles, the 3 angles must add up to the complete thing, 180 degrees. So that's really all you need to know about an angle on a straight line. Next, we're going to look at an angle of 270 degrees and an angle of 360 degrees. Now, an angle of 270 degrees is usually represented with, or commonly represented with, this 3/4 circle. So I'm just going to shade it. So this 3/4 circle. So here's a quarter of a circle, shaded in gray. Now I've shaded 2 quarters. And here's the 3rd quarter. So we have 3/4 of a circle shaded, and that's the representation of an angle of 270 degrees. But the key thing I want you to note is that an angle of 270 degrees is equivalent to 3 right angles. I've drawn 2 right angles, and here's the 3rd one. So it's equivalent to 3 right angles. Think about it. One right angle is 90 degrees. 90 degrees plus 90 degrees plus 90 degrees is 270 degrees. So another way to look at it is 3 times 90, so 3 right angles is 270 degrees. The thing here I'm trying to say is an angle of 270 degrees is equivalent to 3 right angles. An angle of 360 degrees is equivalent to 4 right angles. As you can see, 90 degrees times 4 is 360. Or 90 degrees plus 90 degrees plus 90 degrees plus 90. So 490 basically gives 360 degrees. This is really revision for most of you, but it's important that you remember these angles. You remember that once you see a shape, so you see 2 perpendicular lines and you see an angle drawn this way, you know that the whole angle represented is 270 degrees. So a complete revolution about a point, just like this complete circle here, which I'm showing in gray, is an angle of 360 degrees. It just says that if I start at some point, it takes me a full revolution to get back to that point. Here, an angle of 270 degrees says if I start at some point here, let's use a different color, a point here, I cover an angle of 270 degrees to get to this point. If I continue back to the point I started in, I get a complete revolution, an angle of 360 degrees. And that's all for these 2 angles. And even more revision, acute angles, of course you've covered it. An acute angle is an angle that's less than 90 degrees. Here's an angle of 90 degrees. Anything less is going to be an acute angle. Here's another angle of 90 degrees here. Anything less is an acute angle. So I have 2 acute angles here. You can clearly see them. I mean, the perpendicular is here. The perpendicular to this base is showed as a dotted line, and this angle here lies to the right. You can clearly tell that to get an angle of 90 degrees, I have to start from this red line, for instance, and get to this dotted line. But given that I get to the black line first, I know that the degree of rotation from this base to this black line is less than the degree of rotation from the same base to the dotted line. So therefore, this angle is an acute angle. It's less than 90. Here's another one here. And to the right, we have obtuse angles. These are simply angles that are greater than 90 degrees, but less than 180 degrees. So angles like this and this. I mean, here we have, starting from this point here, that'll be the angle just shown will be an angle of 180 degrees, but it has to be less than 180 degrees and greater than 90. So let me show the, here's an angle of 90, and here is an angle of 180 degrees. So if I'm starting from a point in this line, I have to go beyond the 90 degrees, but without reaching 180 degrees. So this angle here is an obtuse angle. It's greater than 90, but less than 180. Here again, we have another obtuse angle. I mean, this would be 180 degrees, and 90 degrees would be somewhere like here, or rather with the notation, the square. And finally, reflex angles, which are simply angles that are greater than 180 degrees, but less than 360 degrees. So I'll give you an example. In fact, let's consider this. This is 90 degrees. This is 180 degrees. And if I just draw a line here, so let's go with red. So here we go. From here, this point to this point, 90 degrees has been covered. To this point, 180 degrees has been covered, and now we've exceeded 180 degrees. But so as long as the angle formed is less than 360 degrees, this angle is a reflex angle. But once you complete the revolution, it becomes an angle of 360 degrees. So this angle here is a reflex angle. I'll draw another one. Angle here is a reflex angle. Angle here is a reflex angle. It's almost 360, but it's not. I mean, that's pretty much what you need to know about angles. So that's just the fundamentals of angles. Now we're getting closer to the nitty-gritty of trigonometry. And the first thing we're going to look at is a number of trigonometric functions. Now this might not make any sense. Let's start with the word functions. What's a function? Well, just briefly, because I don't want to go out of your scope. If I tell you that y is a variable, y can take any value. Y is some number. X is also some number, but y is 2x. Now what this here is a function. And in this case, y is a function of x. What y? Because y's value depends on x's value. Let me demonstrate. Now if I tell you that x is 1, y is 2. Why? Because y is equal to 2 times x. So if x is 1, y is 2 times x. Y is 2 times 1, y is 2. So y's value depends on x's value. Because if I now say that x is actually 2, y becomes 2 times x, which is 2 in this case. 2 times 2, which is 4. So as you can see, y depends on x. So y is a function of x. So this is why this sort of expression is a function. We're going to be looking at trigonometric functions. For example, sine. So you can have something like the sine of x. The sine of x, where in this case, x is some angle. So these trigonometric functions are generally applied to angles. You can have another one, the cosine of an angle, or the tangent of an angle. We're going to look at these. But just the same way y equals 2x was a function, sine of x is a function. So you can say something like y is sine of x. Now, if I tell you x is 30 degrees, for instance, I can then apply this function sine on 30 to get y. Just the same way, from y equals 2x, I had an x value, and then multiplied by 2 to get y. This sine does something to the x to give you a y value. That's basically what function is. So sine, cosine, and tangent are trigonometric functions. So you can see why they're functions, because something depends on something, something's value depends on another thing's value. So one thing is a function of the other thing. One thing's value is a function of another thing's value. And they're trigonometric functions because they apply to the area of mathematics known as trigonometry. So just to list these functions, one is known as a sine. It's usually applied to angles, the sine of an angle. So it's shortened to sine, the e is dropped. The other function is the cosine, which is shortened to give cos, so the ine is dropped. And the third one, so I should be using an ampersand rather, is a tangent function, which is shortened to tan, as you can see here. So you can have the tan of an angle, tangent of an angle, the cosine of an angle, or the sine of an angle. So those are the three trigonometric functions we're going to be considering. Now we're going to consider what the relationship is between two variables that are related by the sine function. It's going to make sense in a bit, so don't worry about what I just said. So there's an acronym, which is actually a short form for a formula known as SO, CA, TOA. So you're only interested in the groups of three, to be honest, because each group of three letters represents a particular formula. Now the first one is SO. The S represents sine, which I'm going to represent this way, or let's say sine with the E. It says the sine of an angle is equal to the opposite, well, O represents opposite, let me put it that way, and H represents hypotenuse. So what are we talking about? Well, this rule applies to right angled triangles, so you need to keep that in mind. SOHCAHTOA applies to right angled triangles. So for instance, we have this right angled triangle here. You can see the right angle over here. There's an angle here labeled with the Greek symbol alpha. Now, opposite to this angle, we have this side. Adjacent to this angle, we have this side. And the hypotenuse, the longest side of the triangle, the side that's always opposite to the right angle, is here. So we have three sides. I'm just going to highlight them quickly. So this is the hypotenuse, the side opposite to the right angle. This is the opposite side to this angle, because this is the angle we're focusing on. And the third side, remaining side, is the adjacent side. Now, this is how you apply the formula. The sine of alpha, sine of angle alpha, so is equal to the length of the opposite side. That's what O means. Length of the opposite side. So length of opposite side. I'm just going to shorten it with O. So the length of O divided by the length of the hypotenuse. So just to shorten this, I'm just going to have O divided by H. So this is what SO means. It means sine is equal to opposite over hypotenuse. So for this angle alpha, the sine of this angle is equal to the length of this opposite side divided by the length of the hypotenuse. And you're going to see examples shortly that will demonstrate the application of this law. But moving on to the next trio of letters, CA. The C represents the cosine. So for an angle, the cosine of that angle, e.g. this angle alpha here, is equal to the length of the adjacent side divided by the length of the hypotenuse. So in this case, the cosine of angle alpha is equal to the length of this adjacent side divided by the length of the hypotenuse. Moving on to the last trio, TOA, T-O-A. T represents tangent, O represents length of the opposite side, and A represents the length of the adjacent side. So the tangent of an angle, so in this case tangent alpha, is equal to the length of the opposite side, which I'm just representing O, divided by the length of the adjacent side to angle alpha. So that's the length of this opposite side to angle alpha, the opposite side, divided by the length of the adjacent side to angle alpha. Now let's apply SOHCAHTOA to this triangle here and to this angle, which is represented by the symbol theta. So this angle here is known as is a Greek letter and is known as theta. Now, applying SOHCAHTOA, sine of theta is equal to the length of the opposite side, which is the length of this side, that's opposite to theta, divided by the hypotenuse of the triangle. So the length of the hypotenuse, sorry. And the cosine of angle theta is equal to the length of the adjacent side to theta divided by the length of the hypotenuse. And the sine that's always opposite the right angle. The hypotenuse, as you can see, is always opposite the right angle. Finally, the tangent of theta, so I'm just going to squeeze that in here, is equal to the length of the opposite side to theta, so this side, divided by the length of the adjacent side to theta. So I'm going to sketch a right angled triangle. And I'm going to label the sides with their lengths. So I'm going to say this side has a length of 3, so this base here. This side has a length of 4, whatever units. And this side has a length of 5. Now from SOHCAHTOA, I know that S represents sine. I'm looking for the sine of an angle. So I'm going to give you an angle here. I'm going to call this angle alpha. So I'm looking for the sine of this angle alpha. I know that S represents sine, so I'm only focusing on the first three letters, or the three letters associated with S, sine. So, and if you remember earlier, I said the sine of an angle, so in this case sine of angle alpha, is equal to the length of the opposite side divided by the length of the hypotenuse. So it's O divided by H. Now in this triangle here, this case here, we have this angle alpha. As you can see, the length of the opposite side, this side is the opposite side, is 4. The length of the hypotenuse, the side opposite to the right angle, or the longest side, is 5. So sine of angle alpha is 4 over 5, which is 0.8. But you can leave it in the fractional form. That's all. Now for the tangent of an angle. Let's even use the same angle alpha. Now from SOHCAHTOA, so S sine, Ka, where C represents cosine, TOA, T represents tangent. We just focus on this trio because we're looking for the tangent of angle alpha. Tangent of an angle is equal to the length of the opposite side, the length of the opposite side divided by the length of the adjacent side. So let's see. 4 is the length of this opposite side to angle alpha, and the adjacent side is this side here, which has a length of 3. So the tangent of angle alpha is simply 4 over 3. And let's just try out the cosine of an angle. So from SOHCAHTOA, SOHCAHTOA, we're only focusing on this trio here. Ka means the cosine of an angle. So the cosine of angle alpha is the length, emphasis on the length of the adjacent side divided by the length of the hypotenuse. Now if we just go back to the diagram, the adjacent side is 3, because the side that's not the opposite side and not the hypotenuse is 3, and the hypotenuse has a length of 5, always the longest length. So cosine of alpha is simply 3 over 5. So it's that easy. Hopefully you recall that at sometime in the beginning of this video, I demonstrated the expression y equals 2x as a function. I said that, y's value depends on what x's value is. So I said x and y are just variables, but they could be any number. And if x is 1, y is going to be 2 times 1, which is 2. If x is 2, y will be 2 times the new x value, which is 2 times 2, which would be 4. So as you can see, depending on what x is, in this case x is 1, y is 2, in this case x is 2, y is 4. So y's value is a function of x's value. Now it said, this we've been dealing with trigonometric functions, so I'm telling you that the sine, the cosine, and the tangent are trigonometric functions. Just to briefly illustrate the same idea with using the sine, cosine, and tangent, you will need a scientific calculator just for this demonstration. So I'm going to say that instead of y equals 2x, I'm going to say y is equal to the sine of x. And this is going to be very quick. So I'm going to show you that y's value depends on x's value. So this sine is also a function in that sense, because if you get a calculator and you push the button, so it's a button like this, it says sine on it. You push the sine button and then a number, you get some result. So if you wanted to find the sine of, say, if x was 30, you push the sine button and you type in 30 and push in enter or whatever, or the equals to sign in calculator, and you get some result. Now if you do that when x is 30, so if you go to your calculator and you push the sign button, you push 30 and you push the equals to sign or enter, which depending on what calculator you have, you get 0.5 if your calculator is in degrees. If you push, instead of 30, you use 90, and you push the sign button and you type in 90 and you push the equals to sign or equals to button or enter button, you get that y is actually 1. So as you can see in this case, when x is 30, y is 0.5. When x is 90, y is 1. What am I trying to say? I'm trying to tell you, I will show you that y's value varies with x's value. Y's value depends on x's value. Y's value is a function of x's value. And that's just the idea. So you don't need to really know this. Or you do, it helps. But the main idea I'm illustrating is that sine, cosine, and tangent are functions. And they can be used to relate two different variables or two different things. That's all for now. So far I've just given you the theory and just demonstrated a few things, but now we're going to apply what we've learned. So the key thing here is SOHCAHTOA. That is an acronym for formula for the sine, the cosine, and tangent functions. So there's an example. Here we're given a triangle, so we're asked to find the sine, the cosine, and tangent of, so we're given two angles actually, of angle theta and angle alpha in the given right angle triangle. Remember, SOHCAHTOA is a formula for finding sines, cosines, and tangent. They're just grouped in threes. But it's just an easy thing to remember. You can easily say SOHCAHTOA. So we have a right angle triangle here. We have the angle theta here and the angle alpha here. So let's go. So angle theta, the sine of angle theta from the formula given as follows: the length of the opposite side to angle theta divided by the length of the hypotenuse of the triangle, or the right angle triangle to be specific. So O divided by H. So now I think one good thing to do at first is just say, okay, look, for angle theta, the opposite side has a length of 12. The hypotenuse of the triangle, H, is 13. H for hypotenuse. Now we have the opposite side and we have the hypotenuse, so we know the remaining side is the adjacent side to theta. The adjacent side has a length of 5, whatever units. So sine theta is the length of the opposite side divided by the length of the hypotenuse. So that's O, 12, divided by H, which is 13. And that's sine of theta. What about the cosine of theta? Well, from SOHCAHTOA, the cosine, so the length of the adjacent side divided by the length of the hypotenuse. The length of the adjacent side is 5. A is 5. The length of the hypotenuse, H, that's what H represents, is 13. So that's the cosine of theta. So that's 3, 13. The tangent of theta. So let me just make it clear because this could be confused as a 12. Tangent of theta from SOHCAHTOA is the opposite side divided by the adjacent side. So if in case you haven't spotted the trend, it's always the second letter in each trio anyway. It's always the second letter divided by the third one. The second letter divided by the third one. The second letter divided by the third one in each trio. So each trio has been demarcated with these red brackets. So tan is of an angle. In this case, tan of theta is the length of the opposite side to theta divided by the length of the adjacent side to theta. The length of the opposite side to theta, O. So let's do that over A. O is 12 divided by A, which is 5. And we're done with theta. Now we have to do the same for angle alpha. Demarcate this. Now the length of the opposite side to alpha, this is alpha here. Let's use a different color, blue, just for this. The opposite side to alpha has a length of 5. The hypotenuse is just the longest side of the triangle, or the side opposite to the right angle. So let's just note this down. Opposite side to alpha has a length of 5. Hypotenuse of the triangle has a length of 13, whatever units. And the adjacent side, which is the side left, has a length of 12. So, using SOHCAHTOA, we know the sine of alpha is the length of the opposite side divided by the length of the hypotenuse over H, 5 divided by 13. So that's sine alpha. Cos alpha is, from SOHCAHTOA, the length of the adjacent side divided by the length of the hypotenuse of the triangle, A over H. In this case, A is 12. And H, the length of the hypotenuse, is 13. And finally, the tangent of alpha, which is given by the length of the opposite side divided by the length of the adjacent side. So that's O divided by A. O is 5, and A, in this case, is 12. So note, this is everything you need to know in terms of finding sines, cosines, and tangents of angles using right angle triangles, using the formulas embedded in the acronym SOHCAHTOA. But key thing you just need to notice that an angle's opposite side can vary because the opposite side to theta is 12, the opposite side to alpha is 5. So you need to be careful and you need to know which angle you're considering, and you need to find its opposite side and its adjacent side. The hypotenuse of a triangle is always the same, so you don't care. If you consider this triangle, if we're focusing on theta, the hypotenuse is still 13 because it's the side opposite to the right angle. Even if we're focusing on angle alpha, the hypotenuse is still 13 because it's the longest side, or you can just say it's the side opposite to the right angle. So knowing that will help you avoid making mistakes. So that's one example. We're going to try another one. Here's another example. Same question really. Find the sine, cosine, and tangent of angle theta. So we're just focusing on one angle, and we have a different right angle triangle. So here's theta. So first thing to do when you're solving these kind of questions, since you know you're going to use SOHCAHTOA to find the sine, cosine, and tangent when you have a right angle triangle, look at theta. The side opposite has a length of 1. So O for opposite is 1. The hypotenuse, the side opposite the right angle, the square root of 2. So you recall from surds, you can have numbers like this, the square root of 2, which if you punch into a calculator, you get something like 1.4 something. But we can just represent it with the square root of 2. So the hypotenuse of this triangle, square root of 2. We're ignoring units for this case because this example doesn't give units. Units could be cm, meters, because we're talking about lengths. Anyway, the remaining side, which is this side here, is the adjacent side. So it's not the opposite side. It's not the hypotenuse. It's this side here, which is also 1. So the adjacent side has a length of 1. So now we're free to use SOHCAHTOA to work out the sine, tangent, and the cosine of angle theta. The sine of theta from SOHCAHTOA, opposite of a hypotenuse. Cosine of theta, adjacent divided by the hypotenuse. So I'm talking about length, of course. And the tangent of theta is the length of the opposite side divided by the length of the adjacent side. O is 1, h root 2, a is 1, h root 2. So in this case, the sine of the angle is the same thing as cosine of the angle for this triangle. And the tangent over a is 1 over 1, which is 1. So there you have it.